Suppose that you have a system that can be in states labeled by integers 1, 2, etc. State I has energy E sub I. Draw a yellow dash for each state and draw states with higher energies above states with lower energies. The question we would like to answer is this: what is the probability that the system will be found in a state with energy E at temperature T? Imagine that you have n copies of the system that can exchange energy with each other. This is called a canonical ensemble. Even though the system can exchange energy with each other, the total energy of all the systems is held constant at capital E. In addition, the number of systems is held constant. At any given time, the configuration of the ensemble is described by a list of integers n sub 1, n sub 2, such that there are n sub 1 systems in state 1, n sub 2 systems in state 2, etc. We draw a red dot over a yellow dash for each system that is in the state represented by the yellow dash. Conservation of energy requires that capital E equal n sub 1 E sub 1 plus n sub 2 E sub 2 plus . We also have that n equals n sub 1 plus n sub 2 plus . As an example, consider an ensemble of 3 systems with 5 energy levels with energies 0, 1, 2, 3, and 4 units. Let the total energy be 4 units. There are 4 configurations possible. We could have 2 systems in state 1 and 1 in state 5, or 1 system in state 1, 1 in state 2, and 1 in state 4, or 1 in state 1 and 2 in state 3, or 2 in state 2 and 1 in state 3. If we know what configuration an ensemble is in, the probability of finding a system in state I is just the number of systems in state I divided by the total number of systems. For example, the probability that a system is in state 1 is 2/3 for the leftmost configuration, 1/3 for the middle 2 configurations, and 0 for the rightmost configuration. So, which configuration will the ensemble actually be in? To answer this question, we need to understand the concept of the weight of a configuration. The weight of a configuration is the number of ways to distribute n systems such that n sub 1 are in state 1, n sub 2 are in state 2, etc. Consider the leftmost configuration of the screen. How many ways can we distribute 3 systems over 5 states such that 1 system is in state 5 and 2 systems are in state 1? Let 1 system be represented by a red dot, 1 by a blue dot, and 1 by a green dot. There are 3 ways to place a system in state 5. For each of those ways, there are 2 ways to place the second system in state 1. For each of the 6 ways to place the first 2 systems, there is 1 way to place the third system. It appears that there are 6 ways to have this configuration. We call each way a microstate. However, 2 microstates that differ only by exchanging systems within the same state are actually the same microstate, since it does not matter what order we put systems in a state. Thus, there are only 3 microstates corresponding to the configuration with 1 system in state 5 and 2 in state 1. The weight of this configuration is thus 3. We could have arrived at this by noting that there was 3 ways to place the first system, 2 ways to place the second system, and 1 way to place the third system. Thus, there were 3 factorial ways to place 3 systems in various states. However, microstates that differ by permutations of systems within a state are the same microstate. And there are 2 factorial ways to permute the systems in state 1 since there were 2 particles, or 2 systems. And 1 factorial way to permute the systems in state 5 since there was 1 system in state 5. And 0 factorial ways to permute the systems in states 2, 3, and 4 since there were 0 systems in states 2, 3, and 4. Thus, the weight of the configuration is 3 factorial divided by 2 factorial times 0 factorial times 0 factorial times 0 factorial times 1 factorial. In general, the weight of a configuration is n factorial over n sub 1 factorial times n sub 2 factorial times ... because there are n factorial ways to place the systems in the states. But we overcounted by a factor of n sub 1 factorial, n sub 2 factorial ... because microstates that differ by permutations of systems in the same state are the same microstate, and there are n sub I factorial permutations of n sub I objects. We assume that the configuration that the system is actually in is the configuration with the highest weight, that is, the configuration with the most microstates. We are implicitly assuming that all microstates with the same energy are equally likely, so by chance the system will find itself in the configuration with the most number of microstates. We can find this configuration by maximizing the weight subject to the constraints of total energy and total system number. We will maximize the natural log of the weight because it is easier to do. The maximum of the natural log of W occurs at the same values of n sub 1, n sub 2, ... as the maximum value of W. So, take the natural log of W. Use the log rule to break W up into a sum. Use Stirling's approximation to replace terms of the form natural log of x factorial with x times the natural log of x minus x. Later we will need the derivative of n with respect to n sub 1. N can be written as n sub 1 plus n sub 2 plus ... and since n sub 1, n sub 2, ... are independent variables, the derivative is just 1. We will also need the derivative of the natural log of W with respect to n sub 1. Use the product rule, then use the chain rule, then cancel and collect terms. Use the log rules to combine the log terms. Define n sub 1 over n as p sub 1, the probability that a system is in state 1. Now it's time to take the differential natural log of W. Note that n sub 1, n sub 2, ... are the independent variables of natural log of W. We just found that the derivative of the natural log of W with respect to n sub I is negative the natural log of p sub I. The d and sub I are not independent. They are constrained due to the conservation of energy and the fact that the number of systems cannot change. To take these constraints into account, write n as the sum over n sub I. Take the differential of both sides, noting that the change in total system number is 0. Multiply both sides by an arbitrary number, alpha. Now write the energy conservation equation. Take the differential of both sides, assuming that the energy levels can't change and that the change in total energy must be 0. Multiply both sides by negative beta, an arbitrary number. The differential of the natural log of W is equal to 0 for the configuration that maximizes W, so set d natural log of W equal to 0. Add to this the previous equation, alpha times the sum over d n sub I equals 0. Further add the equation, negative beta times the sum over epsilon sub I d n sub I equals 0. Expand the differential of the natural log of W. Collect terms with d n sub 1, d n sub 2, etc. Because we have added all the constraint equations, the d n sub I can now be varied arbitrarily, and thus the only way to make the left-hand side equal to 0 is to force all of the coefficients of the d n sub I equal to 0. For example, we can set the coefficient of d n sub 1 equal to 0. Subtract alpha minus beta times epsilon 1 from both sides. By the way, epsilon 1 is actually E1, and the epsilon should be E's. Multiply both sides by negative 1. Take the exponential of both sides. Factor out an e to the alpha. Use the definition of p sub 1. Multiply both sides by capital N. Write capital N as the sum over n sub I, and note that we have just shown that n sub I can be written as n times e to the alpha, e to the negative beta, e sub I. Divide both sides by n. Factor out an e to the alpha. Solve for e to the alpha. Thus we can replace e to the alpha in the expression for p sub 1, but the expression just arrived. Define the sum in the denominator as z, the partition function of the system. To find beta, remember that we set the differential of the natural log of W plus alpha times the sum over d n sub I minus beta times the sum over e sub I d n sub I equal to 0. Write the sum over d n sub I as dn. Add beta times the sum over e sub I d n sub I to both sides. Divide both sides by beta. Remember that e can be written as the sum over e sub I n sub I. Take the differential of both sides. Use the product rule, and do not assume that the energy levels remain constant. Distribute the summation operator. We just proved that the first term is 1 over beta natural log of W plus alpha over beta dn. From thermodynamics, we know that a change in energy can be caused by a change in entropy, a change in particle number, or a change in volume. We have two equations for dE, and we can set the coefficients of each differential equal to each other. However, we cannot set S equal to the natural log of W because S has units of joules per Kelvin, so we must rewrite the TdS term as kT ds over K, where K is Boltzmann constant, which serves simply as a unit conversion factor. So beta equals 1 over kT, and entropy is K, times the natural log of W. Now go back to our expression for P sub 1. Replace beta with 1 over kT. But we could have derived the same expression for any other state, not just state 1. So the probability of state I is e to the negative e sub I over kT, divided by the partition function. But we want to know the probability of finding a system in a state with energy E sub I. If there are G of E sub I states with energy E sub I, then the probability of finding the system in any of the G of E sub I states with energy E sub I is simply G of E sub I times the probability of finding it in a particular state with energy E sub I. We can rewrite the partition function as a sum over energy levels instead of a sum over states.